Let's start. Today we're going to look into the very last PowerPoint set for magnetism. We're going to talk about inductance, magnetic energy, and force, right? We only have 20 slides, so I'm pretty confident we can finish this PowerPoint set today. Okay. Let's talk about inductance first. I think each and every one of you encountered inductance maybe once or twice before this class. And we all know that if in circuitry we have inductance, usually we have self-inductance as well as mutual inductance. Okay? So in Chinese, there's 自感, 互感. Okay? So today we're going to talk about the origin of self and mutual inductances, and we are going to talk about how to evaluate their values, right? Assume in space we only have one single coil which conducts a steady state current of I1. Okay? So that current loop can indeed generate magnetic field lines, but at the same time, now your understanding to this steady state current conducting closed loop is it actually stores energy in the form of magnetic fields. Okay? So how do we analyze the energy being stored in this loop? You have this wire. Without the current, there's no energy stored. Okay? But now the problem is assuming you have a steady state current of I1, which means, well, you have to devote some work to maintain its operation. And that steady state operation requires energy. Okay? So how do we analyze this problem? We don't really know what's happening before we saw this picture, right? The first moment we look at it, there's already a steady state current. So that's too good to be true. Meaning some energy is already stored so it can operate. And therefore, once you can maintain this current, you have created all the field lines. And that is too good to be true. You have to do work. Okay? So the way we look at it is assume at time 0, initially there is no current. And we gradually add the current up from 0 to I1 over a certain time period. Okay? So let us assume this is time and this is current. So starting from 0, I gradually increase the current to I1. And after it reaches I1, the current is maintained as a constant. So in some temporal duration, we devoted work into this coil so that it can operate at its operational current. Okay? Now, once you have reached a steady state operational current, okay, this current loop has its own area of S1. Okay? So we're asking how many field lines are actually penetrating across the surface area. And that is called the flux. Okay? So here, flux phi 11 means I have current loop 1. I send in the current to a steady state value of I1, and therefore it generates its own field distribution. Okay? So the first subscript 1 means I have magnetic flux density created by current loop 1. But to calculate the flux, I need to perform surface integration. Okay? So the second subscript 1 means the fields created by current loop 1 is now integrated over the surface area of also current loop 1. Okay? So this is B1. The B field created by loop number 1 performing a surface integration over also loop number 1. Okay? So that is flux phi 11, the definition of 11. Field created by the first loop integrated over the surface of the first loop. Okay? And we also define flux linkage. This loop can have several windings. Okay? You can have the same geometry, but now just imagine on this third dimension, you have maybe n windings of the same geometry. So the flux linkage is slightly different from the flux, only in the sense you multiply the total number of windings to the flux, right? So flux linkage is the number of winding multiplied by the flux. No more than that. Okay? So now the definition is very clear. If you only have one loop, you therefore created, well, you stored the energy, right? We'll talk about the energy later. You store the energy somehow, but in the form, you have the self-inductance. So the way to understand inductance is you stored some energy in the form of magnetism. And inductance is a way to evaluate how much energy you have stored. Okay? Basically, self-inductance is your flux linkage divided by the operational current. All right? So the flux linkage divided by I is your self-inductance. This is something we learned in the past. But now you have to ask, this value, the inductance value, does it change as you change your operational current value? It shouldn't change, because once you fabricated this coil, you have picked your material and you decided your geometry. So this loop has its intrinsic behavior, and that behavior is called the self-inductance. No matter how much current you drive it, its self-inductance value should be a constant, right? So inductance is only depending on the geometry and material, but not on your operational current. And therefore, you divide it out, right? Self-inductance, viewed in another angle, is the total number of field lines, right? Divided by normalized to your operational current. So this ratio should always be a constant. Even you increase your operational current, you increase your flux linkage in a proportional way, right? So once you have defined your geometry, you have picked your material, this is basically fixed. Okay? Now, just imagine we have the second coil. Okay? We just added in the second coil. even here, the second coil is not having current flowing across it. So the second coil, C2, is not generating its own magnetic field lines. But in this case, some of the field lines generated by the first loop is going to penetrate across the surface area of the second loop, right? By now, you should understand the flux lines is the way to connect different loops. Just like current is connecting different resistors, right? So magnetic circuitry is using the flux lines to connect between them. They talk, they communicate using these field lines. So in this case, even though the second loop is not really operating, you don't have current. The current value on C2 is 0, but it still shares some field lines generated by the other loop. Okay? Even in this case, you can still calculate flux. Why? Because loop 1 is donating its field lines to me. So over my surface area, I still have some field lines. Okay? For this reason, here, the flux for C2 is called the mutual flux. And it's defined by phi 1, 2. If you still remember, the first subscript tells you which loop is generating the field lines. Phi 1, 2. 1 means loop number 1 is responsible for generating the field lines. But the surface integration is performed over the surface area of the second loop. Okay? So once you see the subscript are different, you know you are calculating mutual flux. The number of field lines crossing my surface area, but all these field lines are created by somebody else. Okay? So whenever your subscript are different, you know you're calculating mutual flux. Self-flux, you would have 1, 1, or 2, 2, or 3, 3. They should be identical. Okay? So mutual flux is the way different circuits, different loops, they're communicating by sharing the flux lines. Okay? Now we have the flux. We also can have the flux linkage. So mutual flux linkage is basically, in this case, phi 1, 2, but multiplied by the number of terms of the second loop. Okay, so this is multiplied by n2. Following the definition for self-inductance, we now can define mutual inductance. Mutual inductance, L12, is therefore the flux linkage divided by the current. Now you have to think, which current should you divide? The current that is responsible for generating the field lines. So loop number 1 is generating the field lines, so you have to divide by its operational current. Okay? So this is very basic. Bigger question is, when can we ignore mutual inductance? So take a look on the blackboard. I gave you 3 loops, right? Labeled C1, C2, C3. When can we ignore mutual inductance? This is telling you self-inductance is always there. Why? Because you generate the field lines. So the field lines you generated must cross your surface area. So whenever you have an operating loop, meaning you store energy in it, right? You always have field lines crossing your surface area. So therefore, you have self-inductance. You know the self-inductance, you pretty much know how much energy is being stored in your loop. But mutual inductance is another story, right? Mutual inductance means, well, maybe one loop is not really operational, but some field lines are given for free. So can you tell me, on the blackboard, C3, C1, and C2, are there loops which might not have mutual inductance? Meaning they don't share their field lines. I can pretty much draw, well, C1 can generate lots of field lines, right? Each field line it generates must pass through its own surface area, right? But maybe just one or two out of 6 are donated to C2, okay? So therefore, you know there is mutual inductance between loop number 1 and loop number 2. What about loop number 3? Does loop number 3 share the field lines generated by loop number 1? They're distanced so far away, right? I actually feel tired by walking this distance, right? So can you answer me, or answer to yourselves? When can we ignore mutual inductance? Some response here? Now you are used to hiding behind the screen, so you feel the pressure now. Huh? Mutual inductance is there whenever you have magnetic field lines being shared between or among different loops. So as long as you have no shared field lines, you don't have mutual inductance. So the most effective way to prevent or to kill mutual inductance is to move the two loops very far apart, right? In this case, I feel tired, so the field line must also feel tired of coming here all this way, okay? So the most effective way is to keep them very distant. Then you can reduce mutual inductance, all right? Now, as we said, we only talked about L12, meaning loop number 1 is responsible for generating the field lines, and loop number 2 is trying to examine, well, how many field lines are provided for me without paying the cost. Right? At the same time, you can also have loop number 2 operating, and loop number 1 is not having current. In this case, you have L21. L21 meaning loop number 2 is having its operational current, generating its field lines, and those field lines, some of them are shared with loop number 1. So the bigger issue is, does L12 equal to L21? I mean, what are your thoughts? L12 equals L21 means equality, right? You like your friend, and your friend likes you equally. Not too much, not too less, right? Just equal. So you're good friends. Mutual, okay? Mutual inductance are supposed to be mutual, okay? So let's prove it. Assume at first we have loop number 1 being operational, right? Only loop number 1 is operational. And we have this knowledge of vector magnetic potential, A, which is defined in this way, okay? If loop number 1 is operational, then we have A1, right? You send in a constant current into loop number 1, it sets up its vector magnetic potential, A1. So you perform the closed loop integration over the differential length over loop 1, and you multiply by its current, its winding number, you multiply by this, divide by this, that is your A1. Okay? But eventually, inductance is more concerned about the flux linkage, right? And then divided by the operational current. So we can formulate L12 using the knowledge of the vector magnetic potential of loop number 1. What am I trying to write here? Curl of A1 is B1, right? L12 is trying to evaluate the flux linkage over the surface area of loop number 2 and counting the number of field lines created by the first loop. Okay? So the field lines are generated by curl of A1, meaning B1, but integrated over the surface area of loop number 2. Well, this, by using Stokes Theorem, curl operation of a vector making a surface integration is equal to the vector itself evaluated over a closed loop. That's Stokes Theorem. Okay? Now we can replace A1 by using this formulation. So L12 is now effectively making a double closed loop integration. And what you're trying to integrate is actually your differential length 1 making a dot product with differential length number 2. So you're just trying to calculate the dot product of the 2 differential length over the 2 loops. So once you see this formulation, you will be very happy. Why? Because dot products are interchangeable, right? You don't really care which one goes first. dl dot dl2 is equal to dl2 dot dl1, right? So why don't we switch the order? Once we switch the order, dl2 dot dl1, that is equal to L21, okay? So this is a very simple mathematical proof to show you that, well, the mutual inductance in most cases are equal. They don't depend on which loop is operational. Okay? So today you buy your friend a lunchbox, tomorrow he'll buy you back the same lunchbox. Okay? Not more, not less. Okay? So basically, I mean, to the daily lives, mutual inductances are equal.